Hello, we are finishing up Chapter 3. The last section is on volume and surface area. Volume is when you multiply to get the interior volume of a figure. So it's everything that's inside of this cube. To find the volume of a rectangular solid, you do length times width times height. So in this picture, it would be 5 inches times 3 inches times 4 inches. The surface area is the area of each side of your solid. So if you were actually to flatten this out, there's the bottom, there's the 4 sides, and then the top. And that's what it would look like. And so you're finding the area of this figure. And to find that area, then on 2 of the sides, you would do length times width. On the other 2 sides, you have length times height. And then width times height. And each of those multiply by 2 because there's 2 faces that are the same area. And add them up and you get the surface area. To find the volume of any figure, you find the area of the base and multiply by the height. So in this weird figure here, if you just found the area of the base, multiply by the height, you've got the volume of the solid. In example 1, we've got 2 blocks of cheese that are selling for the same price. We want to know which block contains the greater volume. So in these blocks, the base is, well, the first one, the base is a trapezoid, and the second one, the base is a triangle. So the area of the base of the trapezoid would be the height of the trapezoid, not of the solid, divided by 2, multiplied by, add the bases. So the height of the trapezoid is 3 inches. And then the lengths of the base of the trapezoid are 9 and 5 inches. So the area of this base would be 21 square inches. I'm going to go ahead over and find the area of the base on the triangular solid. Since it's a triangle, it's 1/2 base times height. Let's see. This one is a... Let's see. It's an isosceles triangle, so we'll use that formula. For an isosceles triangle, that was that really big formula. 1/2 the base times the square root of a squared, that's one of the sides, minus the base over 2 squared. So we want the base of the triangle, that's 6. And then, trying to make some more room, we've got the side, that's 9 inches squared, minus the base, 6 inches, divided by 2 squared. So we'd have 3 inches, and then the square root of 81 square inches, minus 36 over 2, so that would be 18 square inches. And we should end up with 25 square inches for the area of that base. And now we'll go back and find the volume of the trapezoidal figure. So it is the area of the base times the height. And the area of the base was 21 square inches. And the height of the solid is 4 inches. So we have 84, and it's square inches times inches. So inches times inches times inches, that's cubic inches. And then for the trapezoidal solid, again, we have the area of the base times the height of the triangular solid was 3 inches. I think I left off this should have been 25.5 there. Okay. Multiply by 3, and we have about 76.5 cubic inches. A cylinder. Again, you can just find the area of the base and multiply by the height. The area of the base is the area of a circle, pi r squared. Multiply by the height. Then the surface area of a cylinder, you have to think about the fact that the cylinder, if you have a food can, okay, and you take off the paper and roll it out, you've got a rectangle. And then you have 2 circles for the top and the bottom. And so the surface area is pi r squared times 2 for the circles. And then the length of your rectangle is actually the circumference of the circle, 2 pi r. And then times the height. So that's why we have 2 pi r h for the area of the rectangle. Example 2 says a Pearl art supply store sells paint solvent in a cylindrical can that has a diameter of 4 inches and a height of 6 inches. The giant economy size of the can of the same solvent has a diameter twice as large, and the height of the can is the same, and costs 3 times as much as the smaller can. Which is the better deal? So, the first one is, let's see if I can draw a cylinder here. It's not too bad. It says that the diameter is 4 inches. And the height is 6 inches. So the radius would be 2 inches, the diameter divided by 2. And so to find the volume, we've got pi r squared h. So pi, 2 inches, squared, times 6 inches. That is 75 4/10 cubic inches. Now the other can, it says its diameter is twice that. But it has the same height. So the diameter is 8 inches and the height is still 6. So the radius of this can is 4 inches. So we have pi r squared times the height. Gives us 301.4 cubic inches. We're told that the bigger can costs 3 times as much. What we need to find out is how many times larger is it. So if we take the bigger can and divide by the smaller, we get approximately 4. So the bigger can is about 4 times larger than the smaller can. So if it only costs 3 times as much, then the larger can is the better deal. And it says compare the surface areas of the 2 cans. So I'm going to pick up my picture and take it over so I don't have to draw it again. So the surface area for the first one, it is 2 pi r h plus 2 pi r squared. So 2 pi, 2 inches times 6 inches, plus 2 pi, 2 inches squared. So that'll be 2 pi times 12 square inches plus 2 pi times 4 square inches gives us about 100.5 square inches. Then for the other can, for the larger can, we're going to do the same thing. 2 pi, its radius is 4 inches. The height is still 6. Plus 2 pi times 4 inches squared. Got 24 square inches. And I just noticed something I did wrong. Oh, no, I didn't, because it's surface area. Never mind, sorry. And 2 pi 16 square inches. And that'll be approximately 251.2 square inches. And next we have the volume of a circular cone. That is 1/3 times pi times the radius squared times the height. And the surface area of a right circular cone, and what we mean about right circular cone is that the height is perpendicular to the radius. It doesn't do some kind of thing like this. And its surface area is pi r times the square root of r squared plus h squared. Example 3 says, many northern states stockpile salt to use for melting road ice. In one such state, the highway department builds sheds in the shape of right circular cones to store the salt. Current sheds have a diameter of 30 feet and a height of 10 feet. The department plans to build larger conical sheds to hold more salt. The larger shed will have a 10-foot longer diameter. So that'd be 10 plus 30 or 40-foot diameter. And the same height. So still a height of 10 feet. Or they might have the same diameter and a 10-foot greater height. They ask us to find the volume first of each of the proposed sheds. So the first one has a diameter of 40 feet. So that means its radius is 20 feet. And the height is 10 feet. So we'll find its volume. 1/3 pi r squared h and that is approximately 4,187 cubic feet. And the second one has I've got 30-foot diameter. Yes, 30-foot diameter. So the radius is 15 feet. And the height is 20 feet. So 1/3 pi times 15 feet squared times 20 feet. Approximately 4,710 cubic feet. So it looks like the second one would hold more salt. Part B asks us to find the surface area for each. So the first one, it says surface area is pi r square root of r squared plus h squared. And that is approximately 1,404 square feet. And the second one will have pi times 15 feet times the square root of 15 feet squared plus 20 feet squared. gives us 1,178 square feet. So it looks like the second one will hold more and its surface area is less, so that means it should cost less to build. And that's what C asks us, which design seems to be more economical. So we'll say the second holds more salt and the lower surface area implies that it's cheaper to build. So increasing the height to 20 feet seems to be the better design. Okay, and that was our last example, but we do need to go over the volume and surface area of a sphere in case you need that. So the volume of a sphere is 4/3 pi r cubed, and r is the radius of the sphere. So from the very center of the sphere out to the edge. And then the surface area is 4 times pi r squared. Oh, there is a fifth example. I don't have it in my notes. Okay. Metrodelphia, I guess, is replacing existing spherical water tanks with larger spherical water tanks. The Water Commission insists that to provide for future expansion of the city, the new capacity of the tanks should be at least 5 times the capacity of the old water tanks. This is actually example 4. If the city purchases tanks that have a radius that is twice the radius of the old tanks, will these tanks satisfy the Water Commission? So they're not telling us the dimensions of the old tanks or the new ones. It just says that the radius will be twice the size. And so we want to see if the radius is twice the size, will the volume be 5 times that? So, here's our sphere. And we have a radius for the first one. Let's make that the second one so I don't have to draw one bigger than that. And so the first sphere the radius is r, and the second one, the radius will be 2r. So let's see. We find the volume of the first one. The formula was 4/3 pi r cubed. So that's 4/3 pi r cubed. That's it. The volume of the second one would be 4/3 pi, and r is now 2r cubed. So that's 4/3 pi times 8r cubed, or 32/3 pi r cubed. So the question is, will the second one be 5 times the volume of the first? Well, if we just take the volume of the second one and divide it by the volume of the first one, you can see that the pi's go away and the r cubes go away. So now we're left with just numbers. That's a good thing. So 32 over 3 divided by 4 over 3. To divide fractions, we flip the second one and multiply. So you can see our 3's go away. And we're just left with 32 divided by 4. Well, 32 divided by 4 is 8. So it looks like the second ones will be 8 times as large, which definitely satisfies the 5 times as large qualification. Okay, so that finishes up this chapter. Be sure and do your review and email me if you have any questions. And have a good day.